Good afternoon, everyone, and welcome to RISE Learning Machines seminars. I am Olof Mogren from RISE, Sweden's National Public Research Institute, and I am delighted to welcome you to our open weekly seminar on AI and machine learning. Before we begin, I'll start with a couple of housekeeping things. We'll record this meeting, so do get in touch if you wish to be removed from this recording in the after the meeting. Also, I will encourage you to check out our collection of amazing talks on our YouTube channel. And yes, today we are honored to host Lena Stempfle. Lena is currently a postdoctoral researcher at MIT's Healthy ML group, and she is a recent graduate from Chalmers University of Technology, where she defended her PhD earlier this fall under the supervision of my previous PhD colleague, Fredrik Johansson, I should say. Lena's work is regarding missing values at test time and also explainable AIs, and this is applied to domains such as the medical domain. And with this said, I'll just add that the topic today is interpretable machine learning for prediction with missing values at test time. And with this said, I will hand over the screen sharing and the word to you, Lena.
Thank you so much. Let me get this right. All right. Can you see my screen?
Yes, looks good.
Fantastic. Great. Then thank you so much for the kind introduction. You already mentioned my name, and in the following I will present the work I've done as my time as a PhD at Chalmers, because my postdoc time is that long, so not much work has been done so far. The title of my presentation is Interpretable Machine Learning for Prediction with Missing Values at Test Time. And let me start with an example. As you also said before, Olof, I will have all my examples from the medical domain, but none of the algorithms we developed is tied to this. So you can also apply to many different domains like industry applications or education or finance. But for now, we're going to start by saying that machine learning is increasingly used in healthcare to support clinical decisions. And here you can see my cursor too, right? Okay, great. So we can consider the prediction task whether a patient will experience a cognitive impairment diagnosis that's worsened over time or not. And the data that we will use for this has a structured manner. In this case, we have electronic healthcare records, as you can see in the table here, that may include age, sex, education, and something like a medical test result, as the one from a FDG-P PET scan that measures the glucose uptake in the brain, which is associated with the cognitive decline. You don't need to know much about Alzheimer's. This is my running example, so I give you a little bit of background so you can follow the examples I will show in this presentation. And this data will then be fed into a prediction model that learns from the patients that it has seen in the past and how they relate to diagnosis change. So either there was a change or there was no change in cognitive impairment. And once this model was trained, we can apply it to new patients. For example, we have our patient Anna here, and we're able to produce a prediction for her. Most machine learning algorithms expect the input data to be complete. So this table needs to look like it looks right now. So all the measurements are available and observed. However, real-world table data almost always contains missing values. So missing values means that an information is not observed. And the reasons for that can be various. So you either have measurement errors, you have varying equipment, or tests are not being ordered by clinicians for whatever reason. So in this case, for Anna, the PET scan wasn't taken because potentially this machine was not available and there was no free appointment to take this measurement. So we have a missing value. So what this results into is that we not only have missing values at training time, but we also have them at test time. And then these algorithms who are used to have complete data at training time might fail if they don't have certain measurements available at test time. Since the goal is of these prediction models to equip domain experts with tools that helps them for making decisions, it is not only important to have a solid predictive performance, but also allow them to reason how this prediction was made. This is when we introduce interpretability. And interpretability in our context means the ability to understand and to reason how a model arrives at a prediction in ways that is comprehensible to a human. In our example, that would mean that a clinician needs to understand how the prediction was made and how the missing or the filled-in values influence this prediction. And such requirements are also reflected in legal frameworks, as you may know, the EU AI Act, which mandates transparency and accountability and making interpretability not just like a practical, but also regulatory necessity. So moving forward in this talk, we will mainly focus on how we can develop machine learning methods that handle the missing values at test time, meaning at the time when the decision needs to be made, like when the doctors want to apply these algorithms. But we also want the models to be remain interpretable so they can actually enable the clinicians to make informed decisions. I will give you a short introduction to the setup that we are looking on, that we're having. So we focus supervised learning setting where we observe covariates X, which may contain missing values. So these were the NAs in the table before, highlighted in orange. And missingness is indicated by a mask M, and we want to predict an outcome Y. So in our example, there was a change or no change in cognitive impairment diagnosis, which is a classification task, but you can also think of regression tasks. So our goal is to predict the outcome Y using a hypothesis H by minimizing its risk, and that's defined by the expected loss under the joint distribution of X, M, and Y. And it's important to consider or have the assumption that this will remain the same during training time and test time. So consequently, that means that whatever factors causing the missing values during the test time, these very same reasons persist at training. Sorry, again, the factors causing the missingness at training time remain the same at test time. So we must account for the missingness in both of the phases, training and test time. To make this a bit more clear, we can represent X as a masked version of the complete features X star determined by M. So X star up here is what we would like to have, but we don't have. So this one is the complete one with all features are observed and none of them is missing. M is then the mask that describes or indicates which of the values are missing or observed, and X is the actual input that we have available. So you can see here for the first patient, Lisa, the sex value is not observed, so we have 1 here, which means missing, and 0 means observed. On a side note, I should mention that the missingness can either occur missing completely at random, missing at random, or missing not at random, which are 3 different mechanisms that are describing by which the data became missing. And these are discussed in great depth in the literature. So the challenge of missing values in prediction time isn't exactly new, and there's a wide range of methods proposed, has been proposed in the past, but I will show you 3 solutions from previous work and point out their challenges. Let me start with the first one that we call impute then regress. So we have an imputation function I of x that is used to fill in the missing values in x as accurately as possible, which will then produce the x star hat, which is then passed into the machine learning function hc. That is the model that for example, that is trying to predict the cognitive impairment and that requires to have complete inputs. So we will go from the matrix at the left side to the right side where we previously have missing values that we then fill in by some kind of like imputation function. So imputation basically means replacing the missing values. And while imputation is a very powerful approach, this has been widely studied, there are a couple of challenges around it. So we should consider that the missingness itself can be informative. So for example, if a test isn't ordered, that decision already tells us something, right? So the clinician, for example, haven't thought about the necessity to ordering a certain test because they thought it won't be needed for that for the patient in front of them. But if we then would replace that missing value, we would hide the signal that was underlying in this decision. The second one is that imputation usually assumes that the missingness only depends on the observed values, which is in literature called missingness at random. But this assumption can be wrong, and therefore we would introduce bias. So for example, if we look here for Finn, that's the second patient here, if there's a policy that the FDG PET scans are only skipped for all the patients, and then we would impute the value for Finn, we would take the signal away because it's not missing at random. There's a reason why the value for Finn is not available, and the missingness directly reflects the age of Finn in this case. So imputing the scans would be actually misleading. And the third reason why impute and regress might be a bit problematic is that it reduces the transparency. There can be very complex imputation functions, and once we have filled in the missing values with some imputation function, it can be very complicated to reason how the certain value came about, and clinicians don't have the time to dig into every single imputed value to come up with why this value or how this value was computed. A second approach is that we combine the missingness mask M with a simple imputation. So here the predicted age depends on a simple imputation like filling the missing values with 0 or mean imputation. And then additionally, we will provide the model with the missingness mask M as an extra input so the model can still use the information about which values were originally missing. So you would combine those two. However, the consequence of this is that you extend your this extends the input space quite a bit as we combine the X star hat matrix with the M. And if you then think of having many different features, it just becomes very difficult to interpret these in a high dimensional space. And the third very common approach when you want to do predictions with missing values at test time is that you choose machine learning methods that handle missing values natively. So for example, you would have a function that just directly handles the missing values based on the mask M without a separate imputation step. And a common example for that would be the tree-based methods like XGBoost, which is a sample method fitting ensembles of trees. In the specific algorithm, you would learn a default direction in a decision tree during the training time. And then when you come across a missing value test time, it knows which default direction it should follow in the tree. And XGBoost, for example, works very well, but the disadvantage is that it's very limited to tree model classes, and it lacks interpretability because it doesn't provide any information how the default direction was learned. So far, we have seen 3 different approaches, what one can do if you want to make predictions with missing values, but we also have seen some of the limitations of these approaches. But what if we still want to have good predictions and interpretability for our domain experts. So for the rest of the talk, I will focus on this resulting research question: how can we apply interpretable machine learning to predictions with missing values? And to do so, I will go over 4 papers that we have been that were published as part of my PhD over the last 5 years, where I briefly explain the motivations for each of them, the key ideas, and show some results. I will start with the very first paper, where we have performed a qualitative study with clinicians to get their practical insights on the topic, because clinicians, in our case, are considered the end users of the machine learning algorithms. Our goal was to extend the understanding of how clinicians deal with missing values in real-world practices, because it's not so abstract to think of that clinicians need to make a lot of decisions with incomplete information available all the time. So what we've done is that we have performed a survey with more than 50 trauma clinicians about their experience and their preference with test time missingness. So we collaborated with a clinician network in France from Trauma Base. So all these clinicians were expert in emergency care and trauma care. The survey was split into 2 different parts, where we first asked them about their current practice and decision making when they face incomplete information at time-critical environment. You can think of it as people rushing into the ER, the emergency room, and clinicians need to make decisions about what treatment they will get or what are the next steps. And often the lab results are not already available, because you can't wait 24 hours until like all the measurements come back. So they need to make decisions with incomplete input. And the second part of the survey included, or we asked them basically to apply common strategies, the ones that I have just showed you before, for handling missing values in interpretable models in the real-world motivated example, where we took one of these trauma prediction tasks, asked them to apply the methods that I have shown you before as well, and then figure out what were their preferences and how they were actually using the interpretable models. And it was really interesting to see the results, because the first thing that we have figured out is that the respondents prefer not to do imputation with like black box approaches like mice, because they find it very intransparent and couldn't understand how the values came about. So mice is like multivariate imputation by chained equations, where you basically repeatedly predict each variable from the others, and then you create multiple complete data sets for each of the missing value or missing features. And it's not difficult to understand that this might be very overwhelming, especially if you're in a time-critical environment. We have also observed that several of the clinicians claimed to know how mean or zero imputation worked, but then failed to actually use them correctly, even within a linear model in a toy problem. So there's quite a difference between them thinking they know how to use imputation methods and then actually applying it correctly in a certain mathematical setup. And as a last point, the clinicians emphasized the need for methods that actually support clinical reasoning, meaning they preferred models that align with their medical knowledge and the patient history, which is way closer to how they were trained in like medical school about how to make clinical reasons, which also makes a lot of sense. And they would also need to have training on how to correctly interpret and use the machine learning models to enable like a successful implementation and integration into clinical workflow. These were the results from the survey, and we try to use these insights as motivations for our work developing machine learning methods. So in the very first more technical or methodologically inspired approach, we leveraged the fact that missingness in healthcare data often occurs in patterns. So I'm going to walk you through an example, and we'll start by having these 3 different hospitals, and each hospital has, in this case, 3 different patients. Obviously, in real life, they have more, but yeah, bear with me. So each clinic systematically collects slightly different measurements, and these are indicated by the colored ones, and the white ones are the missing values. So for simplicity, we can assume that each clinic corresponds to one unique pattern. So all patients from the blue hospital have the same measurements taken, and the same measurements are missing. Reasons why we can have different patterns for different hospitals, but it doesn't need to be different hospitals. It can also be different wards or individual physicians, or just like different insurance types. If you think of the US, you have like private healthcare insurance or Obamacare or something like this. So since healthcare data is very often very limited, our overarching goal is to use all of the available data. And one straightforward option is to pull all the data and then fit a full model. For example, you can use a linear model. So in this step, the prediction is basically based on all the available data, regardless which variables were measured for a given point. However, we would need to impute the values for these missing ones for each pattern separately, which can already introduce bias and reduce the interpretability, especially if the imputation function is very difficult. And that can hide the unique informative signals that we have in each missingness pattern, because these patterns represent different groups of patients. Staying in the same setting with the 3 different patterns in this case, what is the alternative? How can we make predictions? We can actually have our very first attempt of creating an interpretable model, and that is making use of the missingness that occurs in patterns. And we could basically just train separate model for each of the observed missingness pattern based on the sample from the same missingness pattern. And that is avoiding the need for imputation. So in this case, we would have like 3 different separately trained models, one for blue, green, and other green color. For the new patients then, or if you have a new patient coming in, you can check which of the variables they have available and measured, and which pattern they belong to, and then you can make a prediction based on this missingness pattern.
Question.
Yeah.
So this then requires the missingness pattern to be in this simple form, as like one clinician or one hospital is actually missing the exact same things for all patients.
Exactly.
Okay.
However, in our algorithm, we have a bit more flexibility, so we require a minimum sample size per pattern, because if you only have, let's say, it depends on the data set. I'm just making an example. If you have less than 5 people in a pattern, you can't make a reliable prediction. So there's a minimum sample size per pattern, and if you don't have this, if you don't have enough samples, our algorithm finds the closest pattern. The disadvantage is that you might lose some information, but it's a bit more practical.
Okay.
Otherwise, we would have like unlimited different patterns.
And this also very much limits the data that you can use for training a model, doesn't it?
I mean, in theory, you can have many different patterns. It just becomes a bit more harder to understand. And you need to have like like what I said before, a minimum sample size per pattern.
Yeah.
Okay.
Thanks.
You're welcome. Please feel free to interrupt me if you have any questions. I can also have a few more breaks to allow for questions. Yeah, I might do this. Right, so I was saying you can fit 3 different submodels in this case, but there are a few a few challenges or drawbacks if you do this. So first one is basically come back to what we just said. If you have many different patterns, the results may become hard to interpret because you can't really differentiate each pattern from each other. So their uniqueness from an interpretability point of view reduces a little bit. If you have two samples in sites, you have very high variance, what I just mentioned. So we would need to have a certain minimum sample size per pattern. And what this approach also neglects is that you don't share any information across the patterns, but you can potentially think of that there is some overlapping information across hospitals or different wards. So we might want to share some of the information. Also, this approach is not making efficiently use of all the data available because you only look at one pattern at a time. And that was the motivation for an algorithm that we developed, where we had the goal of wanting to share information between the separately fitted submodels, especially when each missingness pattern only has a smaller sample size, and we still wanted to have a good prediction performance as well. So we basically blended both of these approaches, and we call this Sharing Pattern Submodels, SPSM. So what is happening in this figure? We have submodels for different patterns. These are indicated by the pattern-specific coefficients, which is delta, and then we combine it with a global coefficient theta. So for theta, this is combined, and then you have two different coefficients that you additively combine. And this setup encourages efficient information sharing and provides a quite good trade-off between the predictive power while keeping the variance low. And you still have like the individual patterns, like their uniqueness is still like basically represented. So for a new patient, in this case, the patient has like the blue pattern or like the features that the blue pattern have observed, you will combine it with two different parts. So you have the global coefficients theta plus delta because it's the blue pattern. And then we have, and we add these together to have like the global view of using all the samples, but then capturing what is unique about the specific pattern, which is in this case pattern 1, the blue one. So in the following, I'm going to show you a selection of some of the results that we have in the paper, and I'm coming back to the example that I had before, where we predict the Alzheimer's disease using the ADNI data set, where in this empirical results, we predict a change in ADA13 cognitive score with a regression task. So we report on the y-axis the test R-square values, which indicates how well a prediction aligns with the true outcomes, and the arrow bars are showing the standard deviation across 5 random subsamples. And at the y-axis, we have a data set fraction. So what we see here is that SPSM, that is the orange line, that is our algorithm, together with the impute and regress approach, in this case, it's a rich regression, using mean imputation, they perform very similar. So it's the green and the orange line up here. So we can see that it benefits from sharing the coefficient and it's placing more weight on the shared model. So the theta coefficient is more dominant. Both of the rich and SPSM outperform the PSM, which is the pattern submodel, where you learn separate submodels per pattern. Especially if you have a small data fraction, so the patterns having a too strong focus on the specific patterns is just not beneficial. At the same time, beyond the predictive performance, we can see that SPSM benefits from a lower model complexity, since we learn fewer coefficients, since we share them across the different patterns. So comparing the pattern submodel, where we learn 430 different submodels, we only use 37 plus 21, which is then 58 coefficients, because we have this sharing component between the models. And if we look a bit more broadly, also across data sets, we find that mean imputation often gives us stronger validation performance for ridge regression, XGBoost, MLP, that all depend on imputation. And yet we see that SPSM matches or sometimes even outperforms most of the baselines, while none of these other baselines is dominantly performing well on all the tasks. So one thing I haven't really shown you is how exactly is SPSM interpretable, which we claim to be as well. So SPSM is interpretable because we can expect the pattern specializations for each of the different missingness patterns. And I want to recap that very quickly. So on the left side here, we see the global coefficients theta. So for a new patient, we would only use a subset of theta corresponding to the observed features in that pattern. So these are highlighted by this orange color. And then we add the pattern specializations delta to capture what is unique about that specific pattern. And we also enforce sparsity into delta through L1 regularization. So only the coefficients that have non-zero values actually show up. And these features then highlight which features are important for the specific pattern to make a prediction. And that will then give us the table on the right side here. So for example, we have something that we call pattern 4, where 3 of these biomarkers, A beta, tau, and p tau, are missing at baseline for that specific pattern. And coefficients are formed by combining the shared global coefficient theta with the sparse adaptation delta 4 in this case, because we have pattern 4. Going to make this a bit more clear. So let's look at the coefficients, how they change when we adapt to this pattern 4, where these biomarkers that are quite important for predicting a cognitive impairment are missing. Because without them being available, the model shifts its way to alternative features. So highlighted here in mint, I guess, we can see that the FDG PET scan, which is again this imaging measure, gets a larger coefficient from minus 0.093 up to minus or negative 0.129. So that means that this specific feature plays a bigger role in the prediction under pattern 4 when these 3 biomarkers are missing. And a similar behavior we can see for the brain volume measures like fusiform or ICV, where their importance in the prediction now increases. Interestingly, we can see the opposite for the age feature, that actually goes down in importance. So in the main model, we can see that the coefficient have a positive value, but in the pattern 4, it then changes to a negative value and actually drops down to negative 0.019. So the predictive influence actually decreases when these 3 biomarkers at baseline are missing. So what we show here is that SPSM also allows us to summarize these changes in a quite compact way. So only 5 features that have the specialized coefficients are shown here, which we then argue would it make quite easy, of course, I need training, right? Makes it easier for the domain experts to interpret which of the features increase or decrease in importance when making a prediction for that specific pattern or the patients within this specific pattern. And that should also help not only decision-making, but also in the communication. So to summarize paper A, we've trained these separately interpretable submodels that share coefficients across the different patterns. And we have shown that SPSM matches the best baselines without depending on imputation. And we can also ensure that we have interpretability that we can represent in this compact way that's shown here on the right, where we show the changes of the weight of features when certain features are missing for a pattern. And another result that we show in the paper is that we define conditions where the sharing is optimal, even when the missingness and the outcomes depend on unobserved variables. With that, I'm moving on to the second approach. So as I said before, in the survey, we have learned that the clinicians don't really like to rely on values that they don't understand or they can't clinically reason about. And with that in mind, I want you to follow me in the second approach, or the idea of the second approach, where you focus on interpretable models that rely as little as possible on variables with missing values. So we want to have the focus on the variables that are actually observed. And we have written 2 papers about this. One was a spotlight paper at ICML this year, and the other one at AI Stats the previous year. So before I dive into the method, let me start with an example. So here on the right side, we have a decision tree with the similar tasks as before, where we predict cognitive impairment, but this is a toy example, I should say. That's not the ADNI data. So the very first split in this decision tree would be on a feature like the MRI scan result, which measures the brain volume and brain volume. So if you have a small brain volume, that is indicated with low cognitive function. And in this decision tree, if you have a result that indicates low volume, you go down on the right side and you can immediately make a prediction. That will be here. If the result is not low volume, you would go down on the right side, and the tree asks for the age of the patients. However, what's important here is that these MRI scans are actually missing for 77% of all the patients in the data set. So for these 77% of all the patients, this tree becomes basically uninformative because it relies on a feature that is rarely observed or is actually not observed for them. So if we now can, take a sidestep and maybe not have this problem altogether. So we don't want to do any imputation of missing values. We don't necessarily want to add missingness indicators, or we don't want to rely on specific architectures like the XGBoost that I have shown before. But our goal would be to learn models that simply avoid relying on features that are very often missing, like this MRI scan, for example. So if a feature is missing and it's not essential for a particular prediction, a good model should be able to proceed without it. So that was the hypothesis that we had going into this project. The question that we ask is then, can we learn to minimize the reliance on missing features? And formally, we set this up as the usual machine learning task where we have inputs X, the desired outputs Y, and a loss function. So our goal is to find a model H that has both a small expected loss and a low reliance, and that is denoted by rho of H. How do we define rho? So intuitively, we would say that rho of H measures the probability that a model needs a feature which turns out to be missing. And then we also penalize this reliance by encouraging models not to depend on unavailable or often unavailable features. We have a trade-off parameter here that is alpha, which needs to be bigger than 0. And that controls how much we actually care about avoiding relying on missing values. How we exactly implement that depends on a model class. And I'm not going to go into much detail, but it's all in the paper. But I would rather show you a couple of results that we that we got from these two papers. So let me start with some empirical results. So the overarching goal is to show you that we can actually have a low reliance on missing values, but still perform on par or even better than the standard baselines that use imputation and therefore rely on missing values. So the task in this table again is predicting the diagnosis change in the ADNI data set, where we use 39 features. There are a couple of more results in the paper, but this is what we're focusing now. So the table here on the right shows mainly two things. We have the prediction quality, the AU ROC metric, that's the area under the ROC curve. So the higher the values, the better classification we have. And then we have our newly introduced metric, which is the missingness reliance metric, that's denoted by rho hat, which is the percentage of subjects for which the model uses or imputes at least one missing value. Our models down here are indicated with MA, which stands for missingness avoidance. And I would like to highlight the decision trees here. So MADT, that not only achieves a higher predictive performance than a normal decision tree, which is up here, so 74.1 comparison to 72.7, but it also relies less on missing values than a normal decision tree. So in this case, only 0.1% of all the subjects in comparison to 11.7% rely on missing values when making the prediction. And we can see very similar behavior for a random forest, our random forest down here, and the normal random forest up there. And even for lasso, although we have a slightly lower performance than a counterpart, but it still benefits heavily from avoiding to rely on missing values. And the reason why the linear model has to sacrifice performance a little bit is because it's not contextual. So the trees have this advantage that depending on which side of a tree you go down, it is contextual. So that's why they perform better. And we can also see that the other baselines like MGAM, XGBoost, NeuMess have very comparable predictive performance. So they're all quite similar, but they're heavily relying on missing values or then the imputed values, which is covered in the second column here. Another result that's...
Question?
Yeah.
The MINTY model, I'm not familiar with it. It had a lower reliance, didn't it?
Exactly. So MINTY is also one of that is like the paper B, that's also one of our methods.
Okay.
And what MINTY does, I know the name is not self-explaining, it's missingness and interpretability. You can think of it as a rule-based model where we learn replacements with replacement features within a rule. So the logic goes, if this feature is not available, then you can use this other feature that is available for a specific patient. And that's also the reason why it has quite low reliance, because it's way more flexible in which features you use. And you can have like a certain number of replacements for features within a rule.
Okay, thanks.
Great. I have a couple of slides for that one later if you have more questions, but it didn't make it into that presentation. So another result can be shown for decision trees. So the two figures here are based on the predictive performance, where we show AU ROC again, and the empirical missingness reliance for the life data set, where the prediction task was to predict the life expectancy of people in different countries. And we show the decision tree results here. So as I said before, alpha is our penalization parameter that we can use, or that we use to regularize the model in navigating how much we penalize if the model is using missing values or not. So if this penalization factor is 0, you would just have like a MA decision tree is just a normal decision tree without any missingness reliance regularization. That would be the blue line up here. So on this left side, we can see that for alpha 0, 0.1, and 1, so that's the blue, orange, and green lines, at a tree depth of like 3 to 4 up here, the model captures the data complexity quite well without any overfitting. So these three models are fairly comparable. If we then move over to the right figure here, we can see that for these same models, the missingness reliance varies quite a bit. So row hat actually for the green line has a lower missingness reliance, but if you have a standard decision tree, still like same predictive performance, you rely way more often on features that are actually missing. So takeaway message here is we showed that you can actually achieve comparable predictive performance while relying less on missing values, and you don't need to sacrifice any predictive power in these models. Coming back as a last result to the example from the very beginning, where we have this tree again with the MRI results, I want to show that the decision trees are inherently well suited to handle missing values because of their reliance on features that is contextual. I mentioned this before. We only consider certain parts of the tree and only the observations that are passed through in a certain node that are affected and depending on the values of the features, right? So we illustrate this idea in like synthetic data again, where we still say to diagnose cognitive impairment. And the orange nodes, they indicate that we have missingness reliance, and the blue ones don't have any. You can also see this at the row head is 0. So this tree doesn't have any missing values while this one has. So to make this a bit more clear is that decision tree you have seen before. And that one is purely optimized for currency. You have a UROC value of 0.74. And the first split already includes like this MRI scan that is missing for 77% of all the subjects. So since many patients don't have the scan available, the tree becomes uninformative for them. At the same time, we can actually learn with our algorithm MA decision tree that avoids using the MRI scan as a very first feature in the tree, but rather focus on measurements that are available for all the patients. So age, for example, is always measured. The MMSE, which is a cognitive test score, is also always measured. And then only for the patients or subjects that end up here, we take the MRI scan because the MRI is only after a positive cognitive test measured, because then a clinician already has some indication that the group of patients has like onsets of cognitive decline. So the key idea here is that the MI trees can strategically minimize the reliance on missing values while still exploiting the information structure in the data, since we have this like contextual structure. So to conclude this talk, let's return back to the question we have asked at the very beginning: if we can actually make reliable predictions with missing values at decision time, and also provide insights in how the predictions were actually made. So we can provide helpful tools to our clinicians. And the answer is yes, that we actually can do that. And we have shown that we can build different interpretable models that either make use of the missingness patterns or rely very little on imputation of missing values. And all of these methods still retain competitive performance to their baselines, whether they use imputation or, for example, fit separate submodels. And we have also shown that we have tunable hyperparameters, which we then argue to give back flexibility to different use cases. So for example, a clinician can decide themselves how much they can actually rely on using these missing values, or if it's more strict that they absolutely can't have any in their decision trees. So you have like this trade-off between reliance and stronger predictive performance. If we then look ahead, what could be done next, or what would we like to explore? It's actually that we would like to see how we can integrate these algorithms into clinical workflow. And that doesn't just mean that we have high predictive performance, that we also design interfaces that naturally fit into the clinician's decision-making process, and that allows them to understand how these models work. So we have a follow-up study with the survey with the clinicians in France, where we then have like a pilot study to actually test this in real world. Another interesting idea would be to modify our approaches to time series data, since often the data collection process in healthcare are actually sequential. You're visiting your doctor more often, or you have different lab results over a specific time. So adapting our methods to handle temporal structure would make them way more applicable in real-world decision-making. And I want to point to some work that we have already done, which is not exactly the same, but it hints towards, where we looked in how we should represent patient history in interpretable models for clinical policies. And that was work together with my colleague, Anton, which I haven't focused too much on, but this work is out there as well. And with that, I would like to thank all my collaborators, mainly the people in the Healthy Eye Lab, and specifically my PhD supervisor, Fredrik Johansson, and also the clinicians from Trauma Base and the academic collaborators at INRIA. Thank you so much for listening. If you have any questions, I'm happy to answer them.
Thank you, Lena. Please, everybody, come with your questions.
I have a question, if I may.
Sure.
First of all, thank you very much for a very interesting presentation. This is actually very relevant for me, because with a urologist, I have developed a decision support system for patients with micturition problems. And very much of what you say is highly relevant. And this is a system is for outpatients, actually, so they are supposed to do measurements themselves. And as you can guess, lots of these measurements are useless. So we have to use whatever they come up with. So these imputations, we actually, since a lot of that data is non-numerical, it's really difficult with imputation, because whatever you assume, it will cause lots of bias, unless you use Bayesian methods. And you didn't say so much about Bayesian. You mentioned it at some point a little bit, but that was one of our major candidates. But it turned out actually for us that in this case, nearest neighbor worked quite well. So it was the simplest case that we actually thought about using as for comparison with other methods. But it turned out to work so well in practice that my colleague, the urologist, actually wanted to stick to this method. And it works quite well for explanation, because it gives automatically the most similar cases. But our next step would be to use naive Bayes, which I think could go quite a long way towards this. You didn't mention this method, so my question is, what do you think about these simpler Bayesian methods for this book?
Yeah. Thanks for bringing this up. So we do mention them in our related work part, like in the papers. So we definitely looked into those too, but they didn't make it into the talk. I mean, Bayesian models are very relevant, and they have great advantages as well. I think there are a couple of challenges around it. Like, you need to know a lot about your prior. And in this very first study, the survey with the clinicians, so I should also say, we always focus on the interpretability part as well. So we are considering the view of the clinicians. And I don't know about your clinical collaborators, but what we got from the survey is that even like a linear model is pushing the limits of their understanding quite a lot. So I'm not sure how easily Bayesian modeling is, like how easy it is to understand for a clinician in a time-sensitive setup to reason about a Bayesian approach. But this being said, we thought about this as well, and I think there are a couple of very interesting combinations where you can actually combine the SPSM with a Bayesian learning approach if you have these priors and then you have like different patterns. So it's a very interesting idea. About the do you have a supervised learning setup?
You can say we have a database with known cases. And then the patients are compared to these, and then incrementally new cases are added to the database. So it's a very, very simple, straightforward approach. But it turned out actually to work quite well in practice.
Nice. And the clinicians can also sort of like reason about what you said, like about the nearest neighbors, and it makes clinical sense.
Yeah. They get the table of the most close cases. I think the clinicians so far they want a very simple arguments. They don't want to have some complex logical reasoning, but some straightforward results that they can also show to the patients.
Which makes a lot of sense because they're also like, clinically or legally responsible for whatever decision they make, and also in communication, it helps a lot. That's definitely also what we got from our survey, that the simple solutions are often preferred. Yeah, very exciting.
Okay, thank you.
You're welcome. Thank you.
Do we have one last question from someone? Have you considered other sort of other data sets? You talked a lot about cognitive impairment here. Other illnesses, diagnoses?
Yeah, absolutely. So in all of the papers, we use several different data sets, not only from like the healthcare domain, but also, for example, for getting a credit accepted by the bank. And then you have different patterns of customers. So yeah, these methods are not tied to the healthcare applications, but it was just easier for the talk to have like one running example. And I think this is where most of our motivation comes from, because it's sensitive areas. But you can definitely think of having this in like, I don't know, predictive maintenance in machines as well.
Also an area where you sort of have motivation not to use deep learning?
I mean, depends on how much interpretability matters, for example. Like if someone carries legal responsibility of the decision making, you need to give them autonomy to make the decision or understand the decision, right? And then the interpretable models have quite some advantage in comparison to black box models.
Yeah, for sure. Right. Thank you very much, Lena, for this talk. Welcome back next week, everybody. We'll have Nora Gormelon from Friedrich Alexander Universitet. She'll be talking about self-supervised pre-training for glacier calving front extraction from synthetic aperture radar images. So welcome back then. This will be October 23rd. Thank you so much for today.
Thank you so much for having me.